Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit number 8, Lesson number 8, Quadratic Word Problems. Before we begin, let me remind you that you can find a worksheet and a homework assignment that go along with this video by clicking on the video's description, or by visiting our website at www.emathinstruction.com. As well, don't forget about the QR codes at the top of every worksheet. Scan those codes with your smartphone or with a tablet, and you'll be brought right to the video that goes with that lesson. All right, let's begin. So, for the last few lessons, what we've been looking at is the zero product law, how to solve equations that are quadratics by using factoring. But in this lesson, what we're going to be doing is doing some quadratic modeling. So, modeling problems that naturally have quadratic equations with an x squared, a w squared, whatever, come up, and then solve them using the zero product law. So let's take a look at the first problem. Exercise 1 says, consider a rectangle whose area is 45 square feet. Now it's very important for you to immediately understand what that means, right? The area, a rectangle whose area is 45 square feet. We know that the length is 1 less than twice the width. That's interesting. We would like to find the dimensions of the rectangle. I'm going to switch back to blue. Letter A, if we represent the width of the rectangle using the variable w, then write an expression for the length of the rectangle, L, in terms of w. So what is L? All right, pause the video now and use the fact that the length is 1 less than twice the width to write an expression for the length in terms of the width. All right, well this shouldn't be too hard, right? The length is 1 less than twice the width. Well, twice the width would be 2 times w, and then 1 less would be minus 1. So that's not so hard. Now, letter B says, set up an equation that could be used to solve for the width, and then of course I was inconsistent and changed it to a little w. Let's go back to big W. For the width, big W, based on the area. Well, what do we know? We know that the area is 45 square feet. We also know that area is always length times width, or width times length. It doesn't really matter. So we can combine those two and say, well, the width times the length is equal to 45, or better yet, the width times twice the width minus 1 must be 45. All right? And there's a nice equation that we can solve. Now, there's my equation, and we can certainly solve it for the width, and that's what we're going to do in letter C. It says solve the equation to find both dimensions. So let me just rewrite the equation down here. W times 2w minus 1 is equal to 45. Now remember, there's essentially only 2 equation solving techniques out there that you really know. One of them is solving by using inverses, but that only really works if the equation has the variable in it just once, or you can manipulate both sides so the variable is there just once. All right? And after solving equations by inverses, then you have the zero product law. Please note, there is no such thing as the 45 product law. So here we've got the product of 2 things equal to 45. Please don't set each thing equal to 45. That's just not the way it works. So what I'm going to do is I'm going to use the distributive property first. W times 2w is 2w squared, and then w times negative 1 is negative w. All right? Now, in order to use the zero product law, we really have to have 2 things. We have to have a product, and that product has to be equal to 0. So in order to solve this, we really need to use the additive property of equality and subtract a 45 from both sides. That's going to give me 2w squared minus w minus 45 is equal to 0. And we're finally at a point where we can use knowledge that we gained in previous lessons, i.e. the zero product law, to solve this equation, right? So we're now going to factor this. Okay, please note the first thing we should look for in factoring is a GCF, but the 2, that's not a common factor with the 45 or the negative 1 attached to the w. So the best we can do here is use a little trinomial factoring, right? We know we'll have a 2w and a w, because 2w and w gives me 2w squared. Now that negative 45, that's a bit more challenging, right? It could be negative 5 times 9, it could be positive 5 times negative 9, it could be a whole variety of things. All right, again, what I'm going to do is I'm going to immediately go for the right factorization, which is 2w plus 9 times w minus 5. Let's do a real quick check, and then we'll probably erase the check, right? We'll get a positive 9w there, a negative 10w there. Those two would combine to be a negative 1w, or just negative w, which is what I need. So what I'm now going to do is I'm now going to just erase my check. I'm going to get rid of it. All right, and apparently I'm going to get rid of part of the 9 too. But I'd like to erase the check so I have more room. Now we can finish this problem using the zero product law by setting 2w plus 9 equal to 0, and by setting w minus 5 equal to 0, right? So I'll solve this one by subtracting 9 from both sides and getting 2w equals negative 9, and dividing both sides by 2, just sneaking it in there, getting w equals negative 9 halves. This one's a little bit easier. I'll add 5 to both sides, and I'll get w equals 5. Now, before we find both dimensions, right, because we haven't found both dimensions, right, what we have here is we've got two values for w. Let's talk about this whole why is one of the solutions for w not viable, right? Now, you're probably not going to be surprised if I tell you that the 9 halves is not viable, right? And of course, it's not viable because you can't have a negative width. You just can't do it, right? The width can't be negative. Even though negative 9 halves is a completely fine solution to this equation, it's not a viable solution. So one of the dimensions is 5, specifically 5 feet, and we also have to find the length. Well, the length isn't going to be that bad because the length we know is 2 times the width minus 1. So that's going to be 2 times 5 minus 1, which will be 10 minus 1, which will tell me that the width is 9 feet. Now, by the way, here's a nice check, right? 5 feet times 9 feet is 45 square feet, right? So that helps me kind of check to see if my answer is reasonable. All right, now, there's a lot of setup here, a lot of modeling, and a lot that goes behind this. You know, you have to feel confident in your equation solving with the zero product law, in your modeling, translating English into algebra. So we're going to get more work on these quadratic models and quadratic equations, in future problems in this lesson. Anyhow, pause the video now and write down anything you need to before I clear out the text. All right, so let me do it. Okay, the text is all clear. All right, so let's move on to the next page. Exercise number 2. A square has one side increased in length by 2 inches and an adjacent side decreased in length by 2 inches. If the resulting rectangle has an area of 60 square inches, what was the area of the original square? First, draw some possible squares and rectangles to see if you can solve it by guess and check. Then solve it algebraically. All right, well, one thing I like about the program that I use is it does have some predefined shapes, which is kind of nice. I'm going to change myself into a rectangle here, maybe go into red, and let's draw a square. See, that's not a square. That's just a line. Let's try that again. Let's try a rectangle in red. All right, so let's say that we have this square, okay? And let's say that, let's say we start with a square that's 5 inches by 5 inches. Now, what do they tell me? They tell me that what I've done with this thing is I've changed it into a rectangle, right? And it's a rectangle that had one side increased by 2 inches, right? One side is increased by 2 inches, and an adjacent side is decreased by 2 inches, right? So we would have 5 plus 2, or 7 inches, and 5 minus 2, or 3 inches. Now the area of this new rectangle would now be 3 inches, times 7 inches, which is 21 square inches. Now, what did I know? Well, I knew that the resulting rectangle should have an area of 60 square inches. So clearly, that wasn't the right setup, right? I mean, this isn't equal to 60 square inches. Now, we could continue to try to be systematic about this and try to play around with some more guesses and checks. But I think what I'd like to do is jump right into the algebra. And what I'm going to do is I'm going to do exactly what we did before. In fact, I'd like almost the identical shapes, but this time what I'm going to do is instead of calling it 5 and 5, I'm going to call it x and x. Right now, think about what we then did. We then created a rectangle that was blue apparently, right? And that rectangle then became x plus 2 and x minus 2, right? And then we found its area. And how did we find its area? Well, we found its area by doing x minus 2 times x plus 2. What we really did was 5 plus 2 and 5 minus 2, but in this case, x minus 2 and x plus 2. And what did we know? We knew that x minus 2 times x plus 2, right, that new rectangle, has to have an area that's equal to 60. Now again, just as in the last problem, I want to emphasize something. There is no 60 product law. Right? I can't say x minus 2 is 60 and x plus 2 is 60 because that is going to give me the completely wrong answers. There's a zero product law, okay? Now, in order to use the zero product law, what I want to do is I want to take this and multiply it out. Now notice, these two are conjugates, all right? We could definitely just do our standard double distribution or foiling or whatever, but anytime you have a minus b times a plus b, you always get a squared minus b squared, right? So we get x squared minus 4 equals 60. Now, in order to use the zero product law, I'm going to subtract a 60 from both sides, and I'm going to get x squared minus 64 is equal to 0. Now I can use the zero product law. Now I can use it, right? To use the zero product law, we have to factor, all right? And that will be the difference of perfect squares, right? I'll have x minus 8 times x plus 8. I'll set x minus 8 equal to 0, add 8 to both sides, and I'll get x equals 8. Take x plus 8, set it equal to 0, subtract 8 from both sides, and I'll get x equals negative 8. Now, like in the other problem, x equals negative 8 is non-viable. We should reject it, all right? Just can't happen, which means not our final solution, but our solution right now is x equals 8. Keep in mind that what they want me to do is figure out the area of the original square. So what we now know is that the original square had dimensions of 8 inches by 8 inches. So our final answer here is 8 times 8, or 64 square inches. Again, one thing that's a nice check is you could increase that 8 by 2, giving you 10 inches, decrease that 8 by 2, giving you 6 inches, multiply the two together, and you'd get 60 square inches, which is a good check. Doesn't leave my head very much room on the screen, but it's a good check. All right, so that's kind of a cool problem. I like that one a lot. Anyhow, I'm going to pause the video now and then clear out the text, so write down what you need to. All right, here it goes. Excellent. Let's keep going. All right, we just have sort of problem after problem here. You know, the more that we can do, the better you'll get at this modeling. So let's take a look at exercise number 3. There are two rational numbers. Remember, rational numbers are ratios of integers. There are two rational numbers that have the following property. When the product of 7 less than 3 times the number with 1 more than the number is found, it is equal to 2 less than 10 times the number. Find the two rational numbers that fit this description. Okay, have confidence, right? You know, you read a problem like this and you say, wow, that's a mess. But have confidence that you can string together multiple steps translating the English into equations, getting equations equal to zero, using the zero product law, etc. So let's do it. All right, let's let n be equal to the number. Now I know that there's more than one, so maybe I'll say numbers. Okay, but we're going to model it to just find one, and we'll find both of them in the process. So let's do this. We're looking at a product. 7 less than 3 times the number. So don't worry about anything else besides 7 less than 3 times the number. There's 3 times the number, and then there's 7 less than it. So we're going to find the product of that with 1 more than the number. All right, so there we go. 7 less than 3 times the number with 1 more than a number. The product is found to be equal to 2 less than 10 times the number. Well, here's 10 times the number, and here's 2 less than it. Wow, but there it is, right? There's the translation. Now you just have to have it within you to say, I can do this, I can solve this. Now, in order to solve it, what we have to do is we have to expand this. We have to like get it in sort of standard form. So I'm going to actually FOIL it. 3n times n is 3n squared. 3n times 1 is 3n. Negative 7 times n is negative 7n. And negative 7 times 1 is negative 7. I'm not going to do anything to this side yet. As usual, I've got a couple of like terms here that I can combine. 3n minus 7n is negative 4n. All right. Sorry, it kind of got a little funny looking there. And again, we need to use the zero product law. So to use the zero product law, we need to get everything equal to 0. So I need to get rid of a 10n from this side. And I'm going to do this all at once. I also need to get rid of that negative 2. So I use the additive property of equality to add a negative 10n to both sides. That will combine with the negative 4n to give me negative 14. And I have to add a 2 to both sides, and watch out there, that will be negative 5. Okay? So I'm now at a point really where I was in the last few lessons. I'm now at a point where I can use the zero product law. Okay? So I'm going to factor this. Let's see, is there a GCF? Well, 3, 14, and 5 have no common factors besides 1. So no GCF, so I'll have a 3n and an n. And of course that negative 5 means I either have 1 times negative 5 or negative 1 times 5, and then there's a question of which one goes where. Again, I'm going to write down the correct factoring right away. I'll have 3n plus 1 times n minus 5. And that is right. If we check it really quickly, 1n, negative 15n combined to be negative 14n. Okay, I'm going to move it up here. I'll have 3n plus 1 is equal to 0. All right, or n minus 5 is equal to 0. Subtract 1, 3n is negative 1, divide by 3, and n is negative 1/3. Here we add 5 to both sides, and we get, I'm going to write it down on the same level, n equals 5. Now, pause for a minute, right? Should we reject the negative 1/3? Should we say, that's not viable, got to get rid of it, it's negative? Think about that for a minute. All right, and the answer is no, for a couple different reasons. Number one, they told me there were 2 numbers that fit this description, and I found 2 numbers. Number two, we're just talking about numbers here. We're not talking about the lengths of rectangles or the amount of milk in a carton or anything like that. We're just talking about numbers. So there's nothing wrong about one number being negative 1/3 and one number being 5. All right? I know this was kind of a beast to translate through, but we got through it. So pause the video now, write down anything you need to, and then we're going to keep solving quadratic word problems. All right, here we go. Let's do another one. Okay, find all sets of consecutive integers such that their product is 8 less than 10 times the smaller integer. Oh, and I really should have said all sets of 2 consecutive integers. All right, remember consecutive integers are numbers like 20 and 21, -4 and -3, right? Those are consecutive integers. It's been a little while since we've done consecutive integer problems. So I want to find all sets of consecutive integers such that their product is 8 less than 10 times the smaller integer. So let's use n again. Let's let n equal the smaller integer. Now remember, if we're talking about consecutive integers, then each one of them just gets larger by 1, so n plus 1 is the larger integer. Okay? Now what do we know? We know their product, which is n times n plus 1, is 8 less than 10 times the smaller integer. Well, that's 10 times the smaller. I apparently really like 10 times the smaller, and apparently I also like not being able to write it very well. 10 times the smaller integer, and then that's 8 less than it. Watch out, it's very easy because the 8 comes first in the sentence to think it's this, but that's a completely different expression. That's actually 10 less than 8, or 10 times n less than 8. Anyway, this is 8 less than 10 times the smaller. All right, so now we're almost on cruise control. Not quite, and in fact, one could argue that the algebra in this problem is much easier than the one in the previous one. N times n plus 1 is n squared plus n equals 10n minus 8. All right, we now need to get everything equal to 0. To do that, I will subtract a 10n and add an 8 to both sides. Nothing combines with that n squared, and then n minus 10n is negative 9n. 0 plus 8 is positive 8, equal to 0. Use a little zero product law magic. N and n, minus 1 minus 8, again, a little check, negative 1n, negative 8n gives me negative 9n. That checks. So n minus 1 equals 0, n minus 8 is equal to 0, plus 1, n equals 1, plus 8, n equals 8. Now, that doesn't actually answer the question, all right? Doesn't actually answer the questions, because I want all sets of consecutive integers. So one set is 1, 2. The other set is 8, 9. All right, so we should always make sure we answer the question. You know, sometimes I can get so wrapped up in the algebra, the modeling, the difficulty of the problem, that I forget to answer whatever they're asking. Okay, so it's important to do that always. Anyhow, write down what you need to. I'm going to clear out the text, and then we'll go on and tackle the last problem. All right, here it goes. Okay, final word problem. Exercise 5. Brendan claims that the number 5 has the property that the product of 3 less than it with 1 more than it is the same as 3 times 1 less than it. Show that Brendan's claim is true, and algebraically find the other number for which this is true. Okay, so what I'd ask you to do now is pause the video and try to do both parts of this problem. Show that Brendan's claim about the number 5 is correct, and then try to model this problem algebraically to find the other number for which this is true. All right, let's do it. So Brendan claims that the number 5, let me say n equals 5 and then do a little underline here, has the following property. What's the property? The product of 3 less than it, so that would be 5 minus 3, times 1 more than it, 5 plus 1, is the same as 3 times 1 less than it. Right? In other words, 3 less than 5 is 2. 1 more than 5 is 6. 1 less than 5 is 4. And it looks like 12 is equal to 12. Yeah, so it works. Now, the reason that I like doing this process and writing it out this way is because now as we do it with the algebra, all we have to do is keep track of the 5, okay? So watch, all right? Now when we just have n, not n equals 5, just n, watch how this works. N minus 3 times n plus 1, everywhere there's an underline, everywhere there's a 5, I'm going to put in an n, but everything else is going to stay the same. N minus 3, n plus 1, 3 times n minus 1. All right, we now need to expand this. We'll do a little foiling, so n times n is n squared. N times positive 1 is positive 1n. Negative 3 times n is negative 3n. And negative 3 times positive 1 is negative 3. On this side, we have 3 times n and 3 times negative 1. All right, let's keep going. Well, actually, I suppose before we get it all equal to 0, what we should probably do is combine like terms here. Yeah, we could get everything equal to 0 first. The order there doesn't matter that much. So now let's subtract a 3n from both sides and add a 3. All right, that'll leave me with n squared minus 5n. And look at this, negative 3 and positive 3 cancel out. There's 0. Okay, well, let's do the zero product law on this. Remember, the first thing I always want you to look for when you factor, zero product law or not, is a GCF. And there is a GCF here. There's an n. So I can rewrite this as n times n minus 5. And what's kind of cool is we can see where the 5 comes from, right? We knew that this worked with 5, but here comes the other number, 0. Right, this one we already knew. N minus 5 equals 0, plus 5, plus 5, n equals 5. But really, we wanted the other one. All right, what's really interesting is the other one is 0. Okay, and we could check that by doing exactly the same thing with the description. Okay, I'm going to clear this out, so pause the video now and write down anything you need to. Okay, here we go. Let's finish up the lesson. So this was probably a pretty tough lesson for a lot of people. All right, word problems tend to be a struggle for many, and word problems that then involve the zero product law, a lot of equation manipulation, that's tough too. What did we do? We translated English into equations and expressions. We took those equations and we rearranged them using things like foiling or double distributing. We got the equations equal to 0. Then we had to use our skills in factoring and the zero product law to solve them. That's a lot to put together, but keep at it, and all of the various skills that go into solving these problems will get stronger, okay? For now, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving.